In today's video, we're going to talk about velocity versus time graphs. After watching this video, you should be able to interpret different types of velocity time graphs, be able to calculate the slope of a velocity time graph, and then be able to calculate the area under a velocity time graph, because all those things are going to tell us something, and so we want to make sure we know what that is. So let's get right into it. Graphing a constant velocity. Okay, you'll remember in the previous lesson we talked about that if an object has a constant velocity in a position versus time graph, it will be just a straight line. It'll have a straight slope. Okay. Now we're switching gears here. You'll notice on our x-axis we still have time, yes, but now on our y we're measuring velocity. And so if the velocity is staying constant, and here I have an example of just 10 meters per second, if it's staying at a constant 10 meters per second, you'll notice the line is now flat. Okay, it's just at a constant velocity of 10 meters per second. All right. So in a velocity versus time graph, if the velocity is constant, the line is flat. Okay. If you have a changing velocity indicating a acceleration, okay, because remember acceleration looks at how much velocity changes. So if you have an acceleration, you're going to have a straight line if it's constant. If the velocity is constantly changing at a rate, we'll say, let's say it's accelerating at 2 meters per second. Okay, if it's accelerating every 2 meters per second every second, then you're going to have a straight line that looks like this. Okay. So here you can kind of see this drawn out in a picture. Here the car is kind of slowly getting going, but as time passes and it continues to accelerate, it's getting faster and faster and faster. Okay, and so you have a flat straight line. There is positive and negative velocity, and again, don't let that throw you through a loop so much. It's totally a directional thing. Okay, so if a positive velocity, if you have a positive velocity in our class, typically that means the object's moving to the right, and so you would be graphing things on the plus side of the graph. So here's the 0 and here's the plus, okay, over here, and then there's the negative down here. So both of these objects right here, both of these guys, are moving with a positive velocity. Okay, notice they both are on the plus side of the graphs. On the right here, both of these guys are moving with a negative velocity, indicating that they are accelerating left, if you will. Okay, so it's totally a directional thing, but a negative velocity indicates that basically you have a different direction going on. Okay, so that's the difference between positive and negative velocity, so don't let that throw you through a loop, because most graphs don't graph in the negative, but with these you can certainly see that happening. Speeding up and slowing down. Okay, so if an object is speeding up, the line on the graph will be moving away from the 0 velocity point. And that kind of makes sense. If something is getting more speed, if it's getting more velocity, you'll notice here's the 0 line. And notice both of these red lines are moving away from the 0 line. Okay, the 0 velocity line, so it's getting faster and faster. If an object is slowing down, it will be approaching the 0 velocity line. Notice here this line is started at 9 meters per second. Well, I'm assuming it's meters per second. And now it's slowing down until eventually it would stop. Okay, it would stop moving. And so here the same thing. If it has a negative velocity, it starts real high and it's slowing down until it hits 0. Okay, so speeding up, slowing down, basically it's moving different directions from the 0 velocity line. The shape of a velocity versus time graph, again, reveals information about an object's acceleration. So if you remember in the last lesson, we talked about position versus time, revealed information about the object's velocity. Now, these graphs look at velocity versus time, and so now we can figure out information about the object's acceleration. Okay. The shape of the line on the graph, whether it's horizontal, sloped, really sloped, sort of sloped, is going to describe the object's motion. And so I'm going to draw some pictures for you guys to kind of just give you some examples of things that could be happening. Okay. So this is a constant velocity picture, and it's moving rightward. Okay. So if it has a constant velocity, remember time is almost always going to go on our x-axis, and then I have velocity, I can't spell, velocity on the y, and here is my 0 line. Okay, you make up a number and how fast you want this to go, but I'm just going to say 10 meters per second to kind of go with the example from the first slide. The line would just be totally flat. Okay, and this would be plus, and this would be minus over on this side. Okay, it'd be totally flat because it has a constant velocity. It's going 10 meters per second, no change. It's not speeding up, it's not slowing down, it's just staying at 10 meters per second. Okay, so that's an example of a constant velocity moving in the right direction. A constant velocity moving in the left direction is going to be very similar. Okay, just one little change. Here's the 0, here's positive, here's negative, and I'm going to say here's 10. Okay. If it's moving leftward, it's going to be just a flat line, as flat as I can draw it. Sorry about that. In just a flat line in the negative 10. So it's moving to the left with 10 meters per second. Okay. So again, a lot of students want to think negative means slow down. That's not always the case. The negative piece is basically telling you a direction. Okay. A changing velocity, so now we have an acceleration. Remember, acceleration looks at how much velocity changes. So now we have an acceleration, right? I'm going to make this guy move faster, okay? So the velocity is going to increase. So here's my little graph. Here's time, and I'll call this the 0 line. And let's say it starts from rest. So it starts at 0 meters per second. I'll put plus and minus here just to kind of stay consistent. Let's say it starts from rest, and it's going to just continue to go faster and faster and faster, okay? And so it would look something like this, okay? Notice the slope is relatively consistent as best as I can draw it, and basically this is just a constant acceleration. It's constantly getting faster, if you will. Acceleration, spell it out. All right, and it's moving to the right. How do I know that? Well, or it's accelerating to the right, I should say, because it's in the positive side of this graph. Okay. Now let's take a look at a changing velocity in the left direction. Here's 0, here's positive, here's negative. And again, I'm going to have it start from rest. So it's going to start at 0 meters per second. And if I try to draw my best straight line that I can, this means that it's speeding up to the left. So it started not moving at all, and then it keeps going faster and faster and faster, moving left. Okay. Now this gets a little bit trickier. It says, how about a constant and then changing velocity? So let's make a graph. It might be easier than me trying to explain it. Here is 0. Here's our time. I'm going to have it moving to the right. Okay, so we can do plus. I think that's easier. And I'll say here's 2 meters per second, here's 4 meters per second, and here's 6 meters per second. I'm going to start with the constant. If it has a constant velocity, it's going to be a flat line. And let me change pen colors here so that we can see this a little better. Let's do yellow. So we're going to say it starts at 2 meters per second, and let's say it stays at 2 meters per second until it hits the 6-second point. Okay, and once it hits 6 seconds, all of a sudden it takes off and it starts to increase its velocity. It starts to accelerate. How would I show that? Well, to show that it's accelerating, I want to move away from the 0 meters per second line. And so it would do something like this. Okay? This is a totally legitimate graph. Okay, basically at this point here, when it's flat, it's a constant velocity. And at this part here, it would be speeding up or accelerating, might be a better word to use, to the right. Okay, and it's speeding up. So this is an example of a graph that has a constant velocity in it, and then it speeds up at the end. Okay, slope and the area of a graph. The slope of the velocity time graph represents the acceleration of the object, and the area under the graph shows how much distance the object traveled. Okay, one little side note I will put on this, and let me just change back into black so you can actually see this. If you have a steep slope, I'm not going to write slop like last lesson. Steep slope, if you have a steep slope, it means you have a lot of acceleration. Okay, and then remember, acceleration could mean speeding up or slowing down. Okay, but a steep slope, a lot of acceleration. Small slope equals not much acceleration. And if it's flat, you have none, right? Can I fit this in? I can, sort of. All right, not much acceleration, that's what that says. Okay, so a steep slope, a lot of acceleration, a small slope, not much acceleration. Let's take a look at some different types of graphs, and what I'm really focusing in on is this piece here, the area under the graphs. That area under the graph can be used to determine how far the object traveled in that amount of time. So let's kind of talk about that. Here is a velocity versus time graph. You'll notice, is this object accelerating? The answer is no. How do I know that? Because this line here is flat. Okay, it's flat. It's staying at 30 meters per second from time 0 to time 6. So there's no change in acceleration. But this pinkish or purple pinkish color, whatever you want to call it, with dots in it, that is the area under the graph. And that area under the graph represents the displacement. Remember, displacement is how far the object changed its position, okay, and in some direction too. So I'd call this shape a rectangle if I were to make a guess in terms of what shape it is. Okay, we're going to look at some other shapes. The other ones we want to look at is a triangle and a trapezoid. Here we have a triangle-shaped graph, and you'll notice, what is this object doing? And again, being able to interpret graphs is kind of important. Right? So if you look at this, it starts at 40 meters per second at time 0. What about at time 4 seconds? How fast is it moving then? You all would say 0. It actually stopped moving, okay? So from time 0 to 4 seconds, it started at 40 and then it slowed down. So there is actually an acceleration here, right? Which seems weird to call something that slows down to have an acceleration. But that's the definition of acceleration in physics. Either speed up or slow down. So it slowed down, and basically you'll notice that the area under the graph takes on a triangle shape, this purple with the dots in it. Okay, there's going to be a formula to calculate the areas, and it's nothing new if you've had math class before. Okay, here we have another object where it starts at time 0 and it's not moving, and it basically just accelerates constantly until it gets up to a max speed of, I don't know, maybe 50 meters per second. I'm not certain. But what I'm interested in is, I wonder what is the displacement of this object from 2 seconds to 5 seconds. So you'll notice I started at 2 seconds, I drew a line here, and then until 5 seconds, I drew a line there. And so now we have this purple shaded area, and it's not really a rectangle, it's not really a triangle, this is a trapezoid. Okay, so we're going to use a formula for calculating a trapezoid. And here they are in all their glory. These formulas you probably want to write down someplace that you can quickly refer to them. Some of them, I imagine, maybe all of them, you've seen before. The area of a rectangle is base times height. That's what B stands for. B equals base, H equals height. So base times height, or you could do length times width. They'll get you the same answers, okay, but that's what that is. A triangle, if you're dealing with a triangle shaped thing, it's 1/2 base times the height. Okay, 1/2 base times the height. And a trapezoid is 1/2 base times, and then parentheses, height 1 plus height 2. And I'm going to do examples of all three of these, so you'll get a feel for it in just a second. Okay? So here, let's do maybe I think the easier of the three. Here's a rectangle, right? Hopefully you'll agree with me on that that's a rectangle. And again, remember the formula for a rectangle is base times height. Okay? Here is my base, right down here. Okay, that's my B. And over here, this is my H, my height. Okay, so what is my base? Well, it looks like it's 6, right? It starts at 0 and goes to 6. So I have 6 times, and let's see here, what is my height? Starts at 0 and goes to 30. So what is 6 times 30? I believe that is 180, and the units would be meters, because velocity is measured in meters per second. Okay, so that's kind of another cool thing you can do with these graphs, is you can look at the area under the line to figure out how far the object traveled. Let's do a triangle. Again, the formula for a triangle is 1/2 base times height, or BH. And so I'm going to just basically put some numbers in here, right? 1/2 times, my base goes from 0 to 4, so 4, times 0 to 40, so 40. And if you do that math, I get 80 meters. And so what this is saying is this object traveled a distance, or displaced itself, 80 meters. And that can be determined just by looking at this graph and doing some algebra. The last one, and probably the hardest one, this is a trapezoid. Okay. And remember, the formula for a trapezoid is 1/2 times base times height 1 plus height 2. Okay, so I'm not really concerned with this part here, at least in this problem. Okay, so I start at 1 and I go to 3. So what is my base? My base is going to be 2. Okay, it's a change of 2 spots. So I go 1, 2. So I have a change of 2 seconds. Okay, so my base is 2. I'm just going to drop it down right below here. Okay, times 1/2, which is just 1/2, times height 1. You can call whatever you want height 1, but I'm going to call this piece right here height 1. Height 1 is 10. Okay, so 10 plus height 2 is this over here, and that's going to be 30. Okay, and if you plug all this in your calculator, I get a total displacement of 40 meters. Yeah, this object displaced itself 40 meters over that 2-second time period. Okay? So that takes care of this video. I'll see you guys next time.